Hey, what is up everybody? Today we are going to distinguish between different types of solutions. Sounds easy enough, but there's a lot there. The first thing we're going to do is explain the role of water in the solution process. 2, we're going to write equations for the dissolution of soluble compounds in water. So what happens when we put things in water? How can we describe it in an equation? 3, determine the number of moles of ions formed upon the dissolution of soluble ionic compounds. 4, distinguish between a strong electrolyte, weak electrolyte, and a non-electrolyte. So in this video, I'm going to keep coming back to this awesome simulation where you can make your own solutions. Friday night, see what happens when you make solutions, put things in water. Such a good time. Basically, we're going to talk about, what happens when we put things in water to make a solution, right? It may not seem like you do a whole lot, but a lot is going on in terms of the chemistry. Okay, so first things first. An aqueous solution is just water that contains dissolved substances. Water, substance, dissolved. Now, the solution process depends on the forces of attraction between the solute, or the thing getting dissolved, and the solvent, the thing doing the dissolving. And in many cases, the solvent we're talking about is water. It's often called the universal solvent because it dissolves so many things. Not everything, but a lot of things. I'm melting! Not me though. I don't dissolve from water. Okay, so first, recognize there are attractive forces between the solute particles that are holding those particles together. 2, recognize there are also attractive forces between the solvent molecules. Remember those hydrogen bonds that we saw with water? Hydrogen bonding in between the water molecules. 3, so when you put the thing that's going to get dissolved in the thing that's going to do the dissolving, there are attractive forces between the solute and the solvent. And then 4, we actually make that solution then if the attractions between the solute and solvent are strong enough, the solute will then dissolve into solution. Alright, now a lot of this is really difficult to observe on the macroscopic level. All these forces of attraction. I'm attracted to you! No, I'm attracted to you! I love you, solvent! No, you, solute. Okay, so notice here, originally I've got my giant sodium chloride. And I've got my little attractions of sodium to chloride and chloride to sodium. Solute attractions. And then notice my water molecules in my beaker are attracted to one another. I'm going to show some of those partial charges there. And then I'm going to drop my solute in my solvent to make a solution. And notice the solvent molecules, water, will be attracted to the solute particles, sodium chloride. So I'll just put this in here and see what happens. Whoa, pause it there. The water molecules have sort of pulled the solute apart and dissolved it into solution. Now, when an ionic compound made of ions dissolves in water, the ions separate from one another. This is called dissociation and is a result of the attraction between the ions and the polar water molecules. So let's take a look at this thriller of a video that shows the dissociation of sodium chloride in water. Notice that the water molecules arrange themselves around the sodium ions and chloride ions in such a fashion that the negative end of the water molecule surrounds the positive sodium ions and the positive end of the water molecule surrounds the negative chloride ions. Boom. The hydrogen attracted to the chloride ion, the oxygen attracted to the sodium ion. Dissociation of a soluble ionic compound. Now, what results then is a solution with a bunch of moving charged particles that are able to conduct electricity. And the number of ions that is produced in solution depends on the ratio in the original formula. So if I shake in some sodium chloride, notice that the ions dissociate in a 1-to-1 ratio. Because in the original formula, the ions have a 1-to-1 ratio. Notice though, with calcium chloride, when this solute dissociates in solution, I'm going to get twice the amount of chloride ions as calcium ions because of that 1 to 2 ratio that we see in the original calcium chloride formula. Keep in mind that this also applies to ionic compounds that have polyatomic ions. Notice, for example, in sodium nitrate, we have a 1 to 1 ratio of sodium ions to nitrate ions. Recognize that in an ionic compound, it's the ions that are going to dissociate or separate from one another. The individual atoms that make up the polyatomic ion, which are covalently bonded together, do not separate from one another. But again, the ratio of sodium to nitrate is a 1 to 1 ratio, which we can easily see from that original formula. Now, most covalent compounds, except for acids, which we will discuss in our later unit, dissolve in water as intact molecules. Alright, so for this, I've got a couple of molecules of sugar that are right now, attracted to one another. I'm going to highlight them in yellow so it's easier to distinguish between them and the water molecules. Notice when I put these things in water, the individual molecules will separate. The covalent bonds that make up the sugar molecule are not going to break apart. So when you shake a bunch of sugar into a solution, it's not like you're getting a bunch of carbon ions, hydrogen ions, and oxygen ions. That's an ionic compound. In a covalent compound, you're just going to get your discrete molecules dissolved in solution. Alright, now the last thing we need to talk about here is some quick vocabulary terms. If you put a solute that dissolves in water to give a solution of ions, it will conduct electrical current and is therefore called an electrolyte. Typically, it's your ionic compounds that are made of ions that will conduct electrical current when dissolved in water. And 2, recognize that strong acids, which again we'll talk about in a later unit, so don't stress out about it right now, also are good electrolytes. Just keep it in your mind. So if I shake a bunch of an ionic salt into water, and I take this magical conductivity probe, it will in fact light up. Oh my goodness, it is shining bright. Should get my sunglasses on. However, a solute that dissolves in water to give a solution of molecules does not conduct electrical current and is therefore called a non-electrolyte. Typically, it is your covalent compounds that will not conduct electrical current when dissolved in water. Let's do this same thing, but now shove a bunch of sugar in this solution. And take our conductivity probe. No, there are no charged particles in this solution, and therefore electrical current will not be able to flow. But keep in mind there are some things that will dissolve mostly as molecules, but also partially as ions. And they will conduct electrical current, although not as well as a strong electrolyte will, and so we call these weak electrolytes. Typically, it's your weak acids, which again we will talk about later, just introducing it here, are generally weak electrolytes. So your light isn't going to shine as bright. Shine bright like a diamond! Boom! Check out your references in the description below.